All right. Hello, class. So today we are going to be continuing our lecture on orbital perturbations. Specifically, we'll be talking about the orbital perturbation due to the misshapen nature of the Earth. So let's see, a picture here. Here's the Earth. So the Earth is fairly spherical for most intents and purposes, but it's not perfectly spherical. And that non-spherical nature, this oblateness, this sort of fatness we see here, has a significant effect on the orbital elements over time, typically over longer time horizons than, say, the atmospheric drag. But we'll talk about that and the implications for that for design of spacecraft orbits. So we'll be talking about the implication for things like sun-synchronous orbits, Molniya orbits, tundra orbits, and for things like repeating ground tracks. So let's go to the first slide. Right. So this talk is organized into perhaps what we might call the the boring part of the talk. Boring, which is fairly mathematical. So we talk about the gravitational potential of the Earth and what it actually looks like. And this can be applied to other planets as well, but we haven't mapped them quite as well, their gravitational fields. So we really don't have that much information on them. So mostly this is going to be about the Earth. So we'll focus on the Earth right here. And we'll quantify that by talking about how we map the gravitational potential of the Earth, that mu over r thing we talked about earlier, and how it's actually more complicated than that. And we'll talk about perturbations from the perfect mu over r gravitational potential, and put those perturbations in our RTN framework, where we have those three perturbing forces. Where, if you recall, the R, here's our orbit, here's our spacecraft, our satellite, right? There's our satellite there, and remember, radial is in the direction of the radius. T is, N is out of the orbital plane, perpendicular to that, and tangential is perpendicular to both of those vectors. That's N. So we'll break down the effect of that gravitational potential into those three forces, and then talk about the effect of those three forces on the orbit and the orbital elements, but focusing on the perturbations to the orbital elements of right ascension, so how it's oriented, how that orbital plane is oriented, and the argument of periapse, because those are the two main orbital elements that are affected by the gravitational oblateness of the Earth, the fattening of the Earth. We won't really talk about periodic perturbations, so I shouldn't really have that. Mostly focusing on the secular perturbations. And then we'll talk about the effect of those secular perturbations on mission planning, and specifically sun-synchronous orbits, frozen orbits, and critical inclination. So as I said, the first section, right, of this lecture is relatively mathematical, and then the second part of the lecture is a little bit more applied, I guess you could call it, a little bit more focused on the actual mission planning bit. So that's always a little bit more juicy, I guess. Right. So if you remember from the last lecture, right, we talked about breaking down our disturbing forces, right, into three components: the radial, the tangential, and the normal. Right, so normal to the orbital plane, tangential to motion, sort of, and radial as in pointing towards the Earth or away from it. Right, so we had expressions. We developed expressions for the rate of change of these orbital elements as a function of time. In this case, I have ddt because you can't really put two dots on that I. And how those are quantified by, if we have an expression for these forces, how we can find the rate of change of these orbital elements. Right. So again, we'll be focusing mostly on argument of periapse in this lecture, and on right ascension, because those are the two biggest, the two orbital elements which are most affected by Earth oblateness. As you can see, however, you need to know all three of those perturbing forces, and it's a little bit complicated because the change in right ascension it affects the argument of periapse. And we'll talk about that a little bit more later on. Right. So just to give you an idea of the sort of the significance of these orbital perturbations, there's a lot of them. So this is a nice plot from Gill and Montebrook, where it lists sort of the magnitude, it lists acceleration, right? Oops. List the acceleration, which is a proxy for force, as a function of distance and as a function of orbital elements. So you can see here what we focused on last time was these drag forces, and we had the minimum drag and the maximum drag corresponding to solar mins and solar maxes. But as we also talked about, they drop off fairly quickly as you get farther from the Earth. So the distance from the Earth here in thousands of kilometers, well, we see them dropping off rather quickly. You notice the scale on this, right? We go 10 to the negative 10th, 10 to the negative 5th, 10 to 10, and then 1. So in all of these cases, like when you're relatively far out from the Earth, right, you can see that the most important one is J20, and that's the J2 perturbation. That's the one we're going to be talking about today. Right. And these are the ones we talked about last time. Some other ones we don't talk much about here. So we've got the effect of the moon and the sun. Those get actually fairly significant when you get farther out. They increase as you get farther out, and sort of you would expect. You're getting farther from the sphere of influence of the Earth. There's also these J22, J66, these other. Actually, I think that one is more like J3 in our parlance. Those are also Earth oblateness effects, but we won't be focusing on those in this lecture. Right, but you can see that they're still significant. We'll be focusing on this one, however. And this, as you can see, is the largest orbital perturbation once you get out from the center of the Earth. Now, typically it's energy conserving. So despite the fact that its acceleration there listed as relatively high, it doesn't really, you're not going to crash your spacecraft. Energy conserving. However, it can mess up your orbital planning, and so that's why we need to talk about it. By contrast, we see these other orbital perturbations, the moon, the sun. Those actually are not energy conserving. They can add or subtract energy, and there's like studies which find ways to use the moon's gravity field to boost the energy of a satellite. Solar radiation pressure, well, of course, that's going to depend on how much the cross-section of your satellite looks like. And then we got some other things down here, Venus, Jupiter, and so forth, which don't have that great an effect. So this is the one we're going to be talking about, and you can see it's generally speaking the largest perturbation, and that's why it's so important to talk about. Right, just a recollection. I think I hit on this earlier. We're going to decompose our force into RTN coordinates. N being here perpendicular to the orbital plane. Here's the orbital plane here, and N is perpendicular to that. R is in the radial direction, pointing outwards, and T is just the coordinate normal to both of those two. So what we've got to do is we've got to find the perturbation due to the Earth oblateness, and we have to write it down into that RTN coordinate system. So transferring this Earth oblateness, so remember the Earth here is in the middle, and it's rotating with time, and transferring the perturbations, that gravitational potential, to this RTN coordinate system is a bit tricky. Because, of course, remember the RTN coordinate system is flying around and changing with time as the spacecraft flies around and changing with time. So that's going to be tricky. And so we've got to we're going to have to, of course, average these forces in the end over a period of the orbit and do things like that. Right, so basics, if you may recall, if you were present for the, I think, lecture 2 or something like that, we talked about the nominal magnitude of the gravitational force. So we have this force due to gravity here, which is proportional to, well, actually, I think that should be cubed. It's inversely proportional to the square of the distance and so forth. This is a nominal force due to gravity. So that should be cubed. Because there's an r here for the direction vector. Right? And where did we get that? Well, what we did is we took this sphere, assuming the Earth was a perfect sphere, and we took little sections of that sphere, du, and we took the potential of of your spacecraft at this point, u of d something, d theta, right? We calculated the gravitational potential due to that little slice there, and we integrated it over the whole sphere, right? And because the sphere was fairly uniform, well, perfectly uniform in our assumption, this little slice, when we integrated over the entire sphere, canceled out, or the effect of the force, right, perpendicular to this center Earth satellite line. This force canceled out this force, and so what we got was that we could assume that all of the mass of the Earth was centered at a single point right here, and just use that sort of infinitely large dot to calculate our gravitational force, which is where we got that. All right, we had this symmetry about the R12 line, and that's radial symmetry as well, not just the x-axis, but perpendicular to that as well, if you consider this the x-axis. And so for a spherical Earth, right, we didn't have to worry about integrating gravitational potential quite so much as we will in this lecture, where we have a non-spherical Earth. Right? So where we're going to concentrate is finding this u, right, the u for the non-spherical part of the Earth, and we'll take its gradient to get us our force, and then we're going to put that force into the into those RTN coordinates. So, right, here's a sort of a exaggerated map of what the Earth looks like. Notice the scale here, 15,000 to 1. So that means like, so this is an equipotential surface, right? So essentially, this is the geoid, right? That's what it's called. We'll talk about the geoid a little bit more in a second, which is if the Earth was liquefied or turned into entirely water, yet maintained its sort of density and deformities. This is what the surface of the ocean would look like. And what causes this deformation? Well, there's like, there's a few things. Hold on, let me. Sorry for that. Try to eliminate some extra noise there. So what causes this deformation of the potential surface of the Earth? Well, there's a couple things. The first is that the Earth, right, is not solid, not completely solid. So there's a molten core which has different components. And the molten core causes variations in density. And those variations can change over time. Right, and they can affect the orbit of satellites as well. In addition, of course, we have mountains, right? So let's see, where are our mountains? There's Kilimanjaro, right over here. There's some, I don't know, Himalayas over here. There's Everest. Just generally, there's some denser pockets of the Earth where, you know, mountains, the land mass rises above the sea and so forth. And those cause perturbations as well. So not sure that that's the majority of what's causing these deformations, but it contributes as well. So it's a molten core, and then, of course, land mass is denser than water. So the distribution of land mass changes things as well. So as a result, right, the density field, the gravitational potential field of the Earth is not perfectly spherical, and we get perturbations due to that. This is another sort of higher resolution picture of the same effect right here. So we see here there's a dense spot here, probably due to molten core or something. There's a weak spot here. I'm not sure what's causing that. There's a dense spot over here. It's the same picture as on the previous slide. It's just we have it in false color. So as I said, right, the geoid. Now, technically, the geoid, right, is I should have mentioned, is not just due to gravitational potential, because the Earth is rotating, and so there's a centrifugal force component to the geoid as well. Of course, the centrifugal potential energy doesn't affect us. So technically, we won't be using the geoid, but it's a nice visualization technique. So centrifugal acceleration doesn't affect satellites because they're not tied to the surface of the Earth. They have their orbital energy, their rotation, of course, causes centrifugal force, but that's already accounted for in the orbit, because the orbit is the balance, of course, between gravity and centripetal acceleration, or centrifugal. Right. So how do we account for this non-spherical Earth? Right. So we could hypothesize things, right? Well, the Earth is like slightly distorted due to its rotation, the effect of the moons, and all sorts of things. But in truth, the potential energy, or the gravitational potential energy, the density, the distributions of land mass, all of these things are much too complicated for anyone to theoretically derive. And so it turns out, well, the only reasonable solution is to actually go out and measure, right, how the Earth is composed, the composition of the Earth, right? So we measure it, right? So this is a very, very old field of study, right? Physical geodesy, right? Measures, well, one of the interpretation is measuring the shape of the Earth, right? Which is a bit challenging, of course, because you can measure the height above sea level, perhaps, but what about how the sea level is not perfectly spherical, and so you have to have this geoid, and you measure actually mountains and stuff, the height of mountains from as height above the geoid, height above sea level, right? Here's the sea level, right? So here's the perfectly spherical ellipsoid, and there's some points where the sea is actually below that sphere, and some points where it's above it. Right? But I don't see those points on this picture. Maybe right here. I don't know. So here's the sea level is above the geoid. Right? And so accounting for that, measuring the height of the land distribution of the landmass, it's a very complicated topic. We're not going to talk about it too much. I'll just mention that it's a topic that people study in great depth, but we're not going to worry about it too much. Right? So it's physical geodesy. We're measuring the surface of the Earth from the geoid, and of course surveys and land markers and all of these things are a subshoot of that types of measurements. So here I've got a little introduction to. I mean, none of this sounds terribly exciting. I understand that, right? So of course, well, map makers, right? Physical geodesy, right? They try and make it seem a little bit more exciting. So I think that's the this is the NASA version of trying to make this exciting. So I have trouble making it exciting, so I'm leaving it to NASA here to try and make things exciting. Anyway, so there was Eratosthenes. We'll mention Eratosthenes in a second. Measured the geoid. Triangulation of points on the Earth. Right there, it's moving a little bit too fast. Who are those guys? So there's a little bit. The Earth is a little bit oblate. Tons of practical uses. Yes, this is true. There are tons of practical uses. There's no argument there. So, for example, if I think they have in this one, if you're trying to make a tunnel, right, that goes through, say, the Alps, right, which they did, right, it's a very difficult process, right, because you've got to map a point, right, that will meet up on those two lines, and the curvature of the Earth and so forth. Finding where you are is quite complicated. So where are we? Here we are. So one of the ways they do that is like by tracking the distance between stations, and they can measure like motion of the tectonic plates. There we go. We can measure the wobble of the Earth. This is, in fact, we'll talk about the wobble of the Earth later. And then here we'll talk about Lagos and how it's you can measure that gravitational field, which they just showed there. In fact, so here's a constellation of satellites. Yay! Hooray for geodesy. So, and here actually they're showing the changes in potential. It's very short, like just a second, but what are you going to do? So anyway, right now, of course, we have fancy satellites for measuring the physical geography of the Earth. And we have satellites as well for measuring the gravitational potential of the Earth, right? And I think that's the main takeaway here. Right. So physical geodesy, the mapping of the Earth, but more important for us, the mapping of the gravitational potential field of the Earth. So it was another sort of attempt to make this a little bit more, enjoyable. Give a brief mention, shout out to the first geodetic surveyor, which would have been Eratosthenes, right? And he, people, of course, as I mentioned earlier, right? Everyone in Greek times knew that the Earth was round. Up from Anaximander in 600 BC. Okay, he didn't know. But everyone after that was pretty clear on the fact that the Earth was round. But the only person who actually went out and measured the actual radius of the Earth, right, get a physical measurement of the shape of the Earth, that would have been Eratosthenes of Cyrene. Cyrene, I believe, where was Cyrene? It was at that city south of Alexandria. So Alexandria, of course, Egypt, right? Here's the Mediterranean Sea. There's Italy, right? There's the Mediterranean Sea. Here's Egypt, right? Okay. And there's Alexandria, which had a big library, right? And that's where all the well-educated Greeks would go to discuss things and talk about things. And Eratosthenes was the librarian of Alexandria, right? And his contribution was to okay, there's Alexandria. So I believe, if I remember correctly, and it's been a while since I've looked at this, he measured the distance between Alexandria, right, where he was living, and this colony down here. Now, I want to say that's Cyrene, but I'm not actually sure, so I won't make that claim. But there was a colony down here, right? And I guess I don't know how he measured the distance, right? Dx, right? He measured the distance from Alexandria to that colony, and which was more or less due south of Alexandria. Right, so right along the longitude line, right? So there's Alexandria. There's that city, I'm going to say Cyrene, but I'm not actually sure about that. So he measured that distance, and then he measured the difference in the angle that the sun made. So there's the sun over here. At the same time of day, high noon, at Alexandria and Cyrene. So he dug a deep well there. Oops. Dug a well, right? And he measured that the angle that the sun would make with that well there, and the angle that it would make there. And on that basis, he was able to determine the angle between those 2 points. And so based on the angle and this knowledge of delta x, right, he could calculate what was the radius of the Earth, right? So the circumference of the Earth, right? This distance, right? If you convert this angle to radians, right, that gives you delta theta equals delta x, right? I think so. So, yeah. Let's see. Now, what can I say? Yeah, because the angle in radians, right, gives you that distance. So he could figure out this number, and he got it more or less right. And Eratosthenes, you can see he's a rather bit of a character. Very devoted to his research. In fact, the big story about Eratosthenes, right, was he lived to a ripe old age, and at some point you can see it. He's sort of like he doesn't have any eyeballs here, probably because he's dead. But he went to the story is he went blind, right? He went blind in a certain point in his old age, and they didn't have Braille or whatever back then, and so he decided that if he can't read books, right? He's a librarian. Then life's just not worth living, right? And so in the classic Stoic tradition, he just decided to kill himself, I guess. And the sort of the fashionable way to kill yourself at the time, I guess, for the Stoics was just to stop to control yourself sufficiently to mitigate the passions, so that you waste away. Anyway, that's Eratosthenes, and here's just the illustration of that, where we're measuring the sun at high noon. You get this angle here, and that gives you the radius of the Earth. So the original geodeser, I think that's the word for it, geodeser was Eratosthenes. Nowadays, of course, we're a little bit more sophisticated. And, of course, in this class, we're not interested in the shape of the Earth so much as the shape of its potential field. Right? Shape of U. Now, I should mention, right, and I'll talk about it more later, right, U, right, here's the Earth. U is going to vary not just with the surface of the Earth. We're not just looking at an equipotential surface. We're interested in mapping that for the entirety of space, right? So when we look at U, this is going to be a function not just of, say, latitude, latitude, longitude, but also a function of radius, right? So what's the potential field at this point in space versus this point in space versus this point in space? And the three coordinates that we'll use initially to define that potential field will be latitude, longitude, and radius. Right, so now we're in the modern age, and as modern as it gets in 1976, right? And we notice that our satellites are moving where they're not supposed to move, and so we want to figure out how to predict that motion, right? And so what we do is what seems rational. We launch a satellite. And it's a relatively high Earth orbit, right? 12,000 kilometers, right? So there's not much drag. I won't say there's no drag, but not much, right? So a relatively high Earth orbit. And we launch this satellite up into high Earth orbit, and we watch what happens to it. So we watch it move around. Here's Earth. Here's Lagios. Right? And we predict, of course, right, that it has a standard elliptical orbit. But then, of course, it doesn't, right? It has perturbations, right, due to gravity. They get weaker as you get farther off, but they're more or less the same in terms of direction as a function of radius. And so we measure the actual motion, right, of the satellite and compare it to predicted motion. And the difference between those two we use to fit to a gravitational potential, right? So we sort of map the effect of an arbitrary gravitational potential on the orbit, and then we observe the difference in actual versus potential, and we use it to reverse engineer the gravitational field. Right. So this is Lagios. It looks like a disco ball, right? I mean, there's no getting around that. And why does it look like a disco ball? Well, maybe disco balls look like Lagios. It was launched in 1976, right? So I don't know if disco was created based on Lagios or Lagios was based on disco, but who knows? Anyway, the concept is the same, right? Which is that in each of these little cavities here, we've got a essentially a box, right? And there's like you can prove that if you shine a laser at a box, right, it will come out the same direction it came back in at. So basically, the idea is you put these disco balls in orbit, and you shine a laser at them, and you measure the time it takes for the laser to come back to you, because it'll come back to exactly the same point it started with. Also, this is how like the paint on stop signs and stuff is designed, so that you get these tiny little reflective cavities, and they reflect light back directly at the direction that it comes from, right? Your headlights in particular. So that was the idea. So you reflected laser light back. You found the distance, and then of course the angles that gives you laser. So ranging measurements, that gives you R, and then of course the angle you point your laser at gives you theta or gives you, right, phi and latitude as well. So that was the original Logos, fairly passive system. It was actually relaunched in 1992, so not it was must have worked fairly well. But of course, it has this disadvantage, right? That it doesn't measure the potential field directly, right? It measures the orbit, and then you have to sort of reverse engineer that, invert the problem in order to get the actual potential field, right? So you go from orbit to potential field, which is a bit unsatisfying and prone to error and things like that. And so a later attempt to measure this potential field directly was the GRACE project. And I apologize, I had no recollection of what GRACE stands for. I assume it's gravity. Gravity. Okay, that's the only letter I can guess. But anyway, it's much cleverer, right? Because what it does is you have two satellites, right next to each other, and what it does is it measures as they move through their orbit, right, the change in relative position of the satellites with respect to each other, right? Yeah, relative motion. Right? And if there's a change in relative position, well, A, that's easier to measure without as much noise. So much more accurate, and it directly gives you the gradient of that potential field, right? Because it's relative forces between these two satellites, sort of delta U equals delta F. And so that the GRACE project was specifically designed to measure that potential field and allows us to directly reconstruct these gravitational potentials. So the methods that we describe in this lecture and the methods that are described in Pressing and Conway are based on the assumption that we can measure the gravitational field and fit it to data, and that data is more or less comes from this GRACE project. Of course, there's less fancy methods, survey markers, ocean level variation measurements, sort of more modeling of the problem. These were actually lower orbit, and because, right, you can measure the relative motion, right, that allowed us to do this at lower orbit. Unlike the Logos project, where you wanted to avoid drag. Now the difference in drag between these two satellites is negligible, and so we can measure the field at a much lower altitude. Right. So also they are polar, right, so that you can sweep out the entire Earth as well. Right. So their polar orbit, and the Earth rotates under them, and so you get to map out the entire potential field. And here is the older geodesy, right? You may have seen these all over the place. The U.S. Geodetic Survey, 1965 marker, but they're much older markers from like 1902. I've seen out there. If you climb mountains, occasionally you see these things. And don't move them, or you have to pay $250. So, there you go. Although, it's embedded in concrete in a stone, so I'm not sure how you would move it anyway. And yeah, they're almost always embedded, so I don't think they have to worry too much. Here we just see some of that data that was collected from the GRACE project. This is time variation of those of the gravitational anomalies. You can see the motion, how this changes over years, relative to the baseline. Denser pockets moving, so the ocean level equivalent surface. This is what this is measuring. What the surface of the ocean would look like, that geoid. So motion of the geoid is dense pockets of the molten core move around as the density of the Earth changes and so forth. That's what we're seeing here. And the other picture is more or less the same. It's just the ocean level. And you get less variation here for some reason, probably because the ocean itself tends to move around and compensate for some of those bumps, which you don't get on land. All right. Right, so that's the data, right? So now we have U. Here I write U as a function of R being a vector, right? It's this vector here, right? As I mentioned, it's a bit challenging to compute U as a function of R. You could use machine learning or something like that, but that wouldn't be very helpful. And so what we tend to do is we break down this U, not as a function of R, but as a function of the primary effects on it. The spherical harmonics, we'll talk about it. Phi, which is latitude, lambda, which is longitude, and then the magnitude of the distance, right? So we'll focus on that. So we'll talk about what U is. Then we'll need to compute, of course, its gradient, right? F, and and then we'll be able to calculate perturbations. Right. So as I said right here, we'll be looking at this as a function of its primary harmonics, latitude, longitude, and distance. It just simplifies the process that fits the data better. Mention here, right? Just a definition. Phi is latitude, technically declination from the equatorial plane, right? So latitude, I guess actually, this is 0 degrees latitude. Yeah, so it's latitude, but magnitude, right? So declination. This is I'll give a warning. Some texts, I'm thinking of Curtis, not many others, actually measure this potential field the other way, right? I don't know why, from the North Pole, right? So we'll be using declination or latitude measurements as our phi. But again, Curtis, right, uses this angle. R, which is radius, and then of course right ascension. Now this is right ascension on the Earth, right? So this is not from the first point of Aries. This is from the prime meridian, which is the Greenwich meridian. So let's see, Greenwich is here somewhere. Let's see. I don't see Greenwich, but assuming England was right here, there's Greenwich right here where you have the Royal Observatory, and that's the 0 lambda that's a 0 lambda. So your latitude, your longitude line is measured from there anyway. So this is just longitude. And of course, that's fixed to the Earth, right? So as the Earth rotates around, right, that gravitational potential rotates with it, which of course will complicate our life a little bit because our satellites sort of move in the ECI frame, and this is sort of in the ECEF. So we'll need this in the ECI frame. Well, actually, we need it in the RTN frame, right? But of course, we know how to get from ECI to RTN. We don't yet know how to get from ECEF to RTN. Right. So as I mentioned, this is one of those cases where we derived all these perturbation equations, the RTN coordinate systems, because that seemed like a natural coordinates for perturbing our satellite, perturbing forces. But this is one of those cases where it's not really the natural frame for defining the forces, right? So it simplified our expressions actually a little bit, but now it's going to complicate our life. So we tend to break down, so here's our gravitational potential, basically, right? And we tend to break it down into I would say primary components, right? Harmonics, right? So they're like Fourier functions and things like that. Things that oscillate as a function of latitude, longitude, and we do that because, well, it's easy to fit data to that kind of thing, as we fit data to Fourier transforms as well, right? And so, okay, we got our nominal, right? That's our nominal gravity, that mu over r gravitational potential that we used so often earlier on. So that's the nominal one. And then we've got the zonal harmonics, and we'll talk about what the zonal, sectorial, and tesseract harmonics are. So we'll break it down into parts which vary primarily with latitude, terms which vary primarily with longitude, and terms which vary with or oscillate with latitude and longitude. So we'll talk about each of these. This is the most important. That's the J2 and J3 harmonics. So technically, actually, I should say that the sectorial harmonics actually vary with latitude a little bit as well, but they don't. It's always positive variation. So it's like they get denser here and lighter here. We'll talk about it a little bit more in a minute. Okay. So the first harmonics are the zonal harmonics. Right? So the zonal, I don't know what, not exactly called the zonal harmonics. Must be a good reason. But they're the ones that vary primarily with latitude. Now, in all of these cases, and I didn't mention it, but all of these cases were varying with radius, right, as well. But in these harmonics, the variation with radius is relatively predictable, right? So we don't have to fuss about it too much. It all sort of looks the same. It has this like sort of fraction of the distance from the surface of the Earth to a power, right? And so we don't focus on that as much because there's not as much variation with the radius. Once you've left the surface of the Earth, the primary variation in all of these cases is with latitude and longitude. Now the zonal harmonics are the bands, right? So the Earth, the primary perturbation to the Earth is this J1 perturbation or J2 perturbation. Technically, J1 is mu over r. So we already got J1 in there. This is J2, J3, J4, and so forth. Right. So the primary perturbation, J2, right, is a band around the equator. Right, doesn't vary with longitude. Right, so it's equal thickness. Right, all of these bands don't vary with longitude. Right, so longitude, remember, it looks like that. So they don't vary with longitude, which is important. Right, that's important because, right, remember, your spacecraft is zipping around like that, and if these varied with longitude, right, then the perturbation here would be different from here, and as the Earth itself rotated underneath, right, that perturbation would change from orbit to orbit, and so that would cause all sorts of problems. So this it would cause the opposite of problems because they would tend to cancel out over time. But the zonal harmonics, because they don't vary with where on the Earth you are in terms of latitude, longitude, they tend to cause more problems because they integrate over time a little bit more. Right. So they don't vary with longitude, and so they don't vary much from orbit to orbit, or for, over, which you're in the first orbit versus the second one. Right. Okay, so what do they look like? So basically, we use these sort of harmonic functions, which are given here. Right? So harmonic function here. With maybe that's part of it as well. So those are sort of the basis functions, the sort of nominal, the Fourier functions, for example. And then the data, right? The data comes in from Grace and is used to determine the coefficients. So these functions over here are not based on data. Right, so we have this series expansion from 2 to infinity, and then we just find the coefficients, right, which best fit the observations that we have. Right? And this is true for all of the harmonics. Right? These J2s these JIs are determined by the Geodesy data. The PIs, you see functions here, those are, well, they're similar to Fourier functions or so forth. They're actually Legendre polynomials, right? And here I actually should mention that I mentioned that, right, because we are defining these in terms of latitude, whereas Curtis defines them in terms of phi from the pole, we get this is a function of sine phi, is where Curtis gets as a function of cosine phi. Right? So if we look at this, right, what you expect, say we're taking the first harmonic, right? What you expect to see is that this should be big or positive when phi g is approximately 0, right? And negative, small or negative, when phi is around 90 degrees. Right? Which is a bit misleading because you look at this and, right, you see sine phi of GC, which would be 0 at both of those. No, it would be 0 at here and maximum here at the poles. But actually, that's not what the Legendre polynomials look like. So actually, the Legendre polynomials are, well, they're relatively difficult to calculate. And then you have to, of course, plug in, right, sine phi in for x, right? So I won't go into the Legendre polynomials, other than to point out that, P1 despite looking like it's a function of sine phi, is actually cosine phi. And P2, function of phi, also cosine phi, right? So it's a little bit confusing. Of course, Curtis, right? Curtis is using a different definition for phi, and so he gets that these Legendre polynomials are actually a function of cosine phi, which actually means that these are sine phi. So this is G sine phi in Curtis. So very confusing, but you know, if you have to navigate it, be aware. Right? So in any case, for us, right, the first zonal harmonic looks like this: cosine of phi. So it's has its maximum amplitude at the equator. And at 90 degrees, right, cosine of 90 degrees, what's cosine of 90 degrees? It's, you know, it's 0, right? So that's those are the zonal harmonics. The sectorial harmonics vary primarily with latitude or longitude, right? They do vary with phi as well. Notice the sign there, though, and so it's not quite the same, but it's these are sort of initial ones, but then combined with the variation with latitude. So I here is inclination, not to be confused with an imaginary number. All right, and we notice we get the same dependence on radius, right? And this is going to be common throughout all the harmonics. Same as zonal, and same as the tesseral, which we'll see in a second. So the zonal harmonic, or the sectorial harmonics, are the beach ball looking ones, right? They're the ones that sort of stripe the Earth up. And of course, right, as the Earth rotates, they will vary in inertial space as well, right? So there'll be temporal variation due to Earth's rotation. Because if we convert back to ECI, right, latitude will change with time of a point. So they do vary with latitude, but that term is uniformly positive, and so it's just a magnitude variation in this case. Right. So again, these terms, everything but these terms are fixed, right? They're just basis functions, and the geodesy data determines these coefficients. Geodesy data. Right. Again, many texts more or less ignore the sectorial and tesseral harmonics because they're hard to predict because they rotate with the Earth. They tend to not have those as much secular effect unless you have a repeating ground track, right? That's where, so So here's North America, here's South America, here's Europe, here's Asia, here's Africa, Middle East, right? So a repeating ground track, right, looks like that. So that it repeats from orbit to orbit, doesn't change from orbit to orbit. And so in this case, your orbit is always a sort of above the same points, right? Same latitude lines. And so these perturbations, these sectorial perturbations, add up over time. They're easier to predict and add up over time. They have resonance, is what it's called. Yeah, so we're not going to talk about them again. It does have an effect, but it's too complicated for us to get into. And finally, we have the tesserae harmonics from the Latin tessera, right? Which means tile in Latin. And they're called tesserae harmonics, obviously, because they look like tiles, right? So these are the ones that vary significantly with both latitude and longitude. And here we're using these higher order Legendre polynomials. Notice that's 2 subindexes, right? And with the 2 subindexes, you get these variations with latitude. There you get pluses and minuses, both in latitude and in longitude, right? So these are pluses and minuses in longitude, and these are pluses and minuses in latitude. And again, right, these basis functions are very old. They've been around. The spherical harmonic's been around for. There's a story on that. I just don't remember what it is. But the only thing that's just new from a geodesy perspective is, again, we're taking the data and we're fitting it from Grace or even Lagios to these coefficients. And that's more or less. It's really because it's really hard to predict. You have to do it numerically, integrate these things over an orbit, right? So given the data, you can integrate these over an orbit, but predicting in advance what the effect of these is going to be is really quite problematic. So we'll tend to not concentrate on the tesserae harmonics very much. And in fact, actually, we're not going to concentrate on the sectorial harmonics either. In fact, the only harmonic that we'll really be focusing on in this lecture is that of the zonal. So the first zonal harmonic, or second zonal harmonic, depending on how you're counting. And of course, the first zonal harmonic is mu over r, right? So actually, mu is mu over r plus delta mu. Or sorry, not mu, but u potential. So yeah. Oh wait, hold on. No, that is mu. Sorry. Right. So the potential right here is a combination of the nominal potential and the perturbation, which is this term right here. Right. So how do we get that term? Well, if we just, this is the P2, right? That second Legendre polynomial. And all the rest of the terms are as we talked about earlier. So this is due to what's called the oblateness of the Earth. Oblateness of the Earth, which means that it's slightly fat. It's been sitting around for a while, hasn't been moving very much. It's acquired a little bit of a fat tire. Right. So, I mean, why is that? Well, primarily, I guess the rotational motion of the Earth, right? It's spinning. And so you have some average centripetal acceleration, which is forcing some of that extra mass to accumulate here in the middle. So it's significant. It's not, the ratio of flattening is over, so the delta in, the delta, the 21 kilometers, right, is significant. A 21 kilometer, you can think of it as a 21 kilometer mountain, which exists over the entire equator, right, and above the equator as well. So a 21 kilometer mountain is substantial, right? So 21 kilometer times, of course, 21 times, I don't know how many thousands of miles this is, maybe 6,000 kilometers. 21 kilometers times 6,000 kilometers, that's a lot of mass, right? Extra mass accumulating. And we see that effect, right? That extra mass has extra gravity. Right? And we see that this is the primary effect in the first J2 coefficient, right? Which is 0.001. I mean, it's not huge, right? But compared to every other coefficient, it's enormous, right? So there's the third decimal place, whereas this is in the 1, 2, 3, 4, 5, 6 decimal places. And so the J2 perturbation is at least 1,000 times greater than any other perturbation. Now, the J3 actually does have an effect. We're not going to talk about it, but it does have an effect, and you can use it actually to design repeating ground tracks and frozen orbits and stuff like that. But again, we won't talk about it. The sectorial harmonics and the tesseract harmonics are less important, however. Again, for that reason that the Earth is rotating and they sort of vary with time underneath your orbit. And so they tend to not have these great secular perturbations. They'll have periodic variations, but not secular perturbations. But whereas J2 has a big secular perturbation. Again, these have secular perturbations, but they have small ones, right? These J2s, J3s, and J4s. In fact, if you go back to the let's see, was it beginning of this lecture, right? Again, you can see that J3, the J4, right? Coefficients there. They do show up, but again, they're about 3 orders of magnitude less important. But again, 3 orders of magnitude, there's certain regions where they're more influential than perturbations due to the moon or sun, and of course, in most cases, more important than solar radiation pressure. Just skip ahead. All right. Oh, too far. Here we go. Right. Got some image credits there. Right. Anyway, so we got the we've got our delta U now. So we have the perturbation to the gravitational potential due to J2. And now we're in a position to calculate the effect of that gravitational potential change on force. We want to map that change in gravitational potential to a disturbing force. Right, and how do we do that? Well, okay. So first of all, we're going to simplify this expression a little bit. So we'll plug in here for latitude in terms of coordinates which are slightly more convenient, specifically the z coordinate, right, in ECI coordinates. The z coordinate, right, we're going to try and express this in the ECI frame, and then we'll take its gradient, right? So F equals gradient of U. Right. And that's what we're getting right here. So here's our term, right? And our first step is to do this substitution, where we convert this phi GC to this term here, which is a z component, right? So that's that just plugs in right there using this formula right there. And now we're ready to differentiate it, right? So we'll differentiate it into two variables, r and z, right? R. So I guess I'll give a little different colors now. There's r, 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 and the other color is z, right? So we differentiate u in terms of r, and then that component, right, is in the r direction, obviously, because it's r, right? So remember, there's r direction. And then in the z direction as well, which is r is in RTN coordinates already, so that's good. Z is not RTN coordinates, so we're going to have to convert that later. All right. Anyway, so here we go. We take this this partial with respect to r. This is actually the slightly more complicated one, right? So that term goes over there, right? So we take this, differentiate with respect to r. Well, r again shows up two places, so that's why we have two terms here, right? So if we get to, there's a term with z here. Maybe a different color there. Right, so this term here gets mapped down to take the gradient of that, right? And then, oh, sorry, that's incorrect. That was the easy part. Right, so that differentiating with respect to z gets mapped down there, right? That's the easy part, right? Drop the 2, it cancels this 2, and that's easy. The r is slightly more complicated because it shows up twice, right? It shows up in this term and as r squared in this term, right? So we move these over here to 1 over r squared. And this becomes r cubed. And this becomes r to the 5th, right? And so we differentiate that, and we get that's why the 5 shows up here, and this drops down to the bottom. The exponent increases on the bottom. The negative signs switch, right? So this becomes negative. This becomes positive, and then, well, there we go. That's it. So this term is so this term is already in RTN. In this term, we're going to have to convert to RTN coordinates. By the way, I'm following the older version of this book, so if you're following in the newer Pressing and Conway, these calculations aren't in there. This is all from version 1. I'm following their presentation there. Right. So basically, what we've got to do is we've got to convert E hat Z, right? So this is the coordinate. Here's our RTN coordinates. It's just in the z direction, in the ECI coordinates. So we have to express that E hat Z in RTN coordinates, right? So again, right, E hat Z, fortunately it's in ECI, not ECEF. And so we actually already have the rotation matrices from ECI to PQW, and PQW points to the perifocus, and then we just add an additional rotation to get to the to get from perifocus to the actual RTN. So this is PQW. That's the perifocus, and we need one more rotation through F to get to the RTN. So actually, that'll just get added here to this omega. So again, RTN, right? We just so instead of RPQW to RTN, we just add the plus F there, right? Because that's from perifocus, right, to our satellite. Right, so we get this this coordinates, and so we just write down, right, this is E hat Z, right, equals that, times E hat R, E hat T, E hat N. Right, and so we just find this term, right, it's equal to this times that, this times that, and that times that. And so we have a nice expression here for the E hat Z coordinates, which were originally in ECI, now in this RTN coordinate system. So okay, we're almost done. Now all we've got to do is, we had this expression from the previous slide. Now we've just got to plug in here for an expression for E hat Z. We'll also, we would like to eliminate Z as well, right? So let's make Z. So we're going to take Z and plug in our expression for Z. It'll be initially expressed in latitude, but of course we already figured out how to get rid of latitude, and so we can just write it down in terms of the orbital elements. Okay. And so now we've got our disturbing force, yay, in terms of our orbital elements in the RTN coordinate system, right? And so we can break down our components of force. This is R, this is T, and this is N. And so now we can take those three components of force and plug them into our expressions for changes in the orbital elements. So now we've gone through most of the math here. It's only taken a long time. How long has it taken? An hour and 15 minutes. But here we are. We're ready. Okay. So the first element that we're going to consider is right ascension. Right? So if you remember our formula for right ascension, this is it, right? For last lecture. And so everything we've been doing up till now, right, is obtaining the expressions for R, T, and N. For this orbital element, the only one we need is N. Right? So the only force we need is N, because this is the component of the force normal to the orbital plane, right? The one that changes the angular momentum vector, rotates the orbital plane. Here's our orbital plane, H, right? It's the one that's going to rotate that, right? And this is drawn correctly because it's going to be pulling it down, right, towards this band, right? You can think of like this is a band. It's going to be pulling it down here and pushing it up there. So we plug that force in here, right? And as we see, right, as we rotate through, this is very sinusoidally. It's going to be pulling down up here and pushing up here. So it varies over the period of the orbit. And so we plug that number in, and we get this complicated expression here, right? So these are all constants. We've plugged in here. Notice where is it? R, right? This R term. Right? So we plugged in for the polar equation here. R equals P over 1 plus E cosine F. Right? And that's why we have the E cosines F's there. Right? And that's why we have P here. So these are the things which don't change, right? Fixed. And these are the things, well, also this doesn't change. And these are the things which are going to vary over time, right? Okay. So actually, I got rid of theta because I didn't think it was not helpful. But F, right, cycles from 0 to 360 over each orbit. Right? So this is instantaneous, right? Right? Instantaneous rate of change. And if you remember, right, there are three components to any orbital perturbations. There's the short period, the long period, and the secular, right? So we're not actually interested in how this number is changing, right, at every moment in time, right? What we're interested in is, right, what is the secular change over an orbit? Okay. And so how are we going to calculate that? Well, we're going to average this number over, well, f actually. So theta is omega plus f. And that measures how far you are from the equator, right? So if you remember. Okay. So to calculate those, we look at the rate of change of omega as a function of angle, right? So we're going to try and calculate that. It's assisted by the fact, right, that our angular rate of change, right, is a constant, right? This is a Kepler's something or other law, right? The angle or the area that's been swept out is constant, and so we can actually figure out what that number on the denominator there is. So we're going to take the rate of change as a function of angle and then integrate that over one period, or 0 to 2 pi. So there's Kepler's third law. Here we've don't forget the r squared, right? So we just move that r squared to the other side. So of course r also varies with time, right? I should mention that, but right. So now we have this this convenient expression here for the change with angle expressed here as a function of that angle, right? So here we've done theta equals omega plus f, right? And so f equals theta minus omega, right? So this was f. Okay. So we look at that expression. This is fixed. And we want to integrate this over time. Right? D theta. Integral of that expression over a period, which is 0 to 2 pi. And then the average rate of change will divide by 2 pi. So this will hopefully give us the average rate of secular perturbation. So this is the only one we're actually going to explicitly do the integral of. All the others I'll just give you the answer. Why? Because it's complicated and time consuming and so forth. Here it's tractable to some extent. All right, so we're integrating. There's a term which multiplies everything, and then there's two terms over here, right? There's this term and this term, and so we get, right, sine squared. We multiply that out. We get this easy term, and we get the more complicated term right here. Right. So the integral of sine squared, if you remember your trig integrals, right, looks like that. Right, the integral of sine squared over a period, right, is the area of those two bumps, which is pi. Yeah. So this term is just pi. Now these terms is more complicated. Here we're going to use this double angle formula here that we may have seen also in our trigonometry books from high school or whatever. And so actually we're going to break this into two pieces. Specifically this piece and this piece. Now if we look at these pieces, we have to integrate both of them, right? Integral is linear, so we can break out the integral over each. This doesn't change, right? So we pulled that out of the integral. If we look at sine cubed, right? Sine cubed, right, doesn't look like this, right? Sine cubed looks like the cube of a sine, and it retains its sign, right? And so this integral over this part cancels this integral over this part, and so, right, so positive negative, right? And so they cancel each other out, and so the integral over an entire period is just 0. Right? So that produces that 0. And the same thing happens with sine. Well, this is positive through the whole thing, but we have this cosine term, which is, right? So, right. So if we break out this cosine term, well, it's equally positive and negative over this interval, and so this term, right? This term is canceled by this term, right? And this term is canceled by this term, right? And so when you integrate it out, both of these terms come out to 0, and we have that this big, horrible, awful-looking integral, right? If you just integrate it out, it actually just comes out to pi. And so this is almost an exam problem. I should put this on the exam because it comes out to a very nice number, pi. We love exam problems that come out to pi. And so we do that integration. We find that the average rate of variation of the right ascension is just actually these secular terms given here. In fact, it's one less because we can just drop off the pi. Right? That's all that happens. So that cancels that. And so we just get this nice clean term right here. Right. And so, well, that's the variation with theta. And so now we're going to look at the instantaneous rate of variation, but averaged over an orbit, right? And so we're going to look at sort of that rate of variation, the slope of this line, right? So omega dot as a line averaged over an orbit, right? So and for that we just we convert back, so 1 over n, and so that's d theta. Oh, sorry, not 1 over n times n, which is d theta dt, and then the thetas cancel, and there's omega dt. So we had this term, and now we're going to multiply it by n. Here, n showing up there. N, remember, is square root of mu over a cubed. Okay. And so we get this term here, which we can use to calculate the rate of change of the right ascension. Actually, same. So sorry about that, just getting a little bit more coffee here. So, yes, I expect many of you will be getting coffee at about the 1.5 hour point in this lecture. So, what have we got? So we have now that the rate of variation averaged over an orbit of the right ascension of ascending node. So remember, right ascension is measured as at the point, this is the first point of Aries, that the ascending node makes with the first point of Aries. There's right ascension. So the ascending node, the point at which it rises above, from below the equator to above the equator, that's the right ascension. So what's going on here? Well, a couple things we can notice, right? Varies with inclination. Maximum at inclination of 0. So maximum at an equatorial orbit. So max for equatorial. And 0 for a polar orbit. Right. Its sign is negative, right? Sign is negative, which means it's decreasing as long as you're not in a retrograde orbit. If you're in a retrograde orbit, of course, it's increasing. And the reason for that, well, we can sort of see that here, right? So you're flying around in your orbit, right? Like that. And what you find, right, is that there's a little bit extra pulling you down, right? Pulling you down towards the equator so that you get to the equator a little bit earlier than you otherwise would. So when you get to the other side, right, you get to the equator a little bit earlier than you did the last time. And likewise here, right, it may be easier to visualize, right? When you're down here, you get a little bit of a pull towards the equator, and so you get to the equator a little bit earlier than you did on your last orbit. Right? And of course, the point at which you get to the equator is the right ascension of the ascending node. And so if you're getting there a little bit earlier, right, that means your right ascension is changed by a negative amount. It's going that way. Of course, if you were in a retrograde orbit, right, looking like this, right, the opposite would be true. So you're if you're in a retrograde orbit, you're moving like that, and you're below the equator. You're getting to the equator a little bit earlier, and so your deltas looks like that, right? And so actually, in a retrograde orbit, your deltas are positive. What else can we say about it? It's never 0 except at the equator. You can think of it, some people think of it like a top, right? So the Earth is spinning, it has an angular momentum vector, and there's a torque on that angular momentum, right? It's not really a torque because, of course, it's not a rigid body, but it's sort of like a torque, a force pulling that about sort of perpendicular to the angular momentum, pulling that down. Is it a torque? Put a question mark there. And so we know what happens when you torque an angular momentum vector. It goes in the direction perpendicular. Right. Yes. Slightly depends on A and E. So that's in right. P equals A 1 minus E squared. And this, of course, depends mu over A cubed. So it also depends on A and E, right, through that. Yeah. So physically, intuitively reasonable. Large. The change in right ascension of ascending node is non-trivial, right? Very non-trivial. So here we see it as a function of inclination. Also, remember, 0 for polar orbits. And largest in magnitude when you're near equatorial. And so when you're near equatorial orbit, well, it depends on how high you are up. The farther out you are, the less of a problem this is, right? So higher, lower. So lower orbits get this have this effect more pronounced. This is at h equals 0. And at that h equals 0, for an equatorial orbit, this can be as large as 10 degrees per day. Right? 10 degrees per day. Right? So per day. Wow, that's a big change. Right? So do a couple orbits, your right ascension of ascending node has been changed by 10 degrees. Now, which brings up the question, and it can't be made 0 except if you are in a polar orbit. You can't get rid of it. Can't get rid of J2 nodal progression, right ascension nodes. So that means you can't have an orbit which is fixed in right ascension, which seems like it might be a problem, right? And it is for certain reasons, but then it brings up the question of, right, who cares? What missions would require you to have a fixed right ascension? Now, if this was a class, I would ask people what to name some possibilities, and they probably couldn't think of any, unless they knew. But the primary effect, I would say, there's two, right? There's also, well, we'll talk about it later. But the one I'm talking about today is the effect on repeating ground tracks. So what is a repeating ground track? Right, I guess that's the first question. So this is the points over which you're over on the Earth's surface, right? So the ground tracks typically for a satellite looks sort of like a spirograph, right? And they look like that. And then the next time they're like that. The next time they're like that. The next time like that, right? So they don't typically, unless you're careful, they don't repeat. Right? However, it's desirable for certain, it's generally desirable to have a repeating ground track for several reasons. The first of which is you always know where you're going to be able to communicate, or where you're going to be able to map, or you're going to be able to survey. It would be kind of annoying if you design, say, a communication satellite, which was, this is already sort of orange, a communication satellite designed for, I don't know where that is, India maybe, Pakistan. Designed for India, Pakistan, and then the ground track, right, after a while, popped up over to the middle of the Pacific Ocean, where it's not doing much good, right? Desired, and this is the drift. The drift and right ascension. So this is a problem, right? And so typically we design, it's often nice to design orbits with repeatable ground tracks so that they stay over the same point on the Earth. Now there's two components to this, right? The first is that, of course, you're at ECI coordinates and the Earth is rotating under you, right? So you're rotating like that, and the Earth is rotating like that. So that in the ideal case, right, in an arbitrary case, arbitrary period, so period of the orbit, the ground track wouldn't repeat. However, if you were clever and you made your period equal to 1/2 day, right, then you would be, the Earth would rotate half a revolution while you did one orbit, and so you'd appear over a different point on your first orbit, and then your second orbit, right? So you go like that, right? So you'd be your perigee would be over one position on the first orbit, and then another position on the second, but it would return to the first position on the second orbit. So perigee, for example. So that's 1/2 day. And of course, the best example of repeating ground track is geosynchronous. That's where your ground track looks like. Let's say this is North and South America. Your ground track looks like this. It's like a point. Right? Doesn't move at all. So that's geosynchronous. But of course, not everyone is in geosynchronous. So if you want a repeating ground track, you have to make your period a fraction of the Earth's sidereal day. And sidereal, right, slightly different. So sidereal day is slightly different than 24 hours because the 24 hours accounts for the motion of the Earth during that day, right? So it gives you an extra couple seconds, right? Or minutes, actually. I forget how many. Difference between sidereal day and actual day, sidereal day. I have to look that up. Anyway, so this is like a standard thing. Create a, so ignore here delta L2, right? You just make your period equal to a fraction k over j of and these cancel, right? Your period divided by the sidereal day equal to a fraction. So t over te equals k over j for some fraction. And then eventually it'll repeat, right? And so when will it repeat? It'll take k days to repeat and j orbits to repeat, right? That's basically it. So if you choose j equals 1 and k equals 2, or k equals 1/2, for example, then it'll take a half, or maybe j equals 2 and k equals 1, then we get this situation. K equals 1, j equals 2. 2 orbits in one day. Right? However, of course, why are we talking about this now? Because omega dot changes the situation, right? Changes the situation. So basically, the change in right ascension over one period alters this equation, right? So if right ascension is changing over a period, then you have to take that into account. So this is change in right ascension, and this is basically change in those longitude lines. So this is rotation of the Earth, and this is what we've been talking about, J2 perturbation. Okay. And so actually you want the sum of these two multiplied by the number of orbits to equal an integer times the rotation of the Earth, so 2 pi radians. And so, right, you've got to well, we can just move that over to the right-hand side, right? We got to solve this equation. Maybe this will be known. This is known, of course, sidereal day. And then we would choose our inclination, our eccentricity, and things to make this a repeating ground track. Make this an integer multiple. Okay. So this is the major application, or perhaps one of the most important applications of that change in right ascension. Yeah. Here's another repeating ground track, the Shinzhou 4, and you can see how you could sort of measure this like 1, 2, 3. We don't know how many days this is though, so we can't really say what k is. But how many days? Well, if we know how many days this is, we know k, and then we can figure out what j is. So again, the application being, right, we would like to make sure that we always have access to, say, a communication. Actually, I think this is the launch site. Anyway, it's from Sven's Space Place. So plug for Sven's Place. Right. So that's right ascension. It's not actually as well known as the second orbital perturbation due to J2, which is that of argument of periapse. And that we'll talk about more. But it's required for that because, as you see, if you may recall, our formula for the change in argument of periapse has change in right ascension in it. Right? So we couldn't solve this equation if we didn't already have that expression. Okay. So we needed that change for right ascension because it factors in, for other reasons as well, but mostly because it factors into this expression for argument of periapse. So remember, the argument of periapse is where, with respect to the equator, your periapse is. So if this is changing, right, that means your argument of periaps will move from the northern hemisphere gradually to the southern hemisphere, which may be advantageous for, say, communication satellites. Yeah. Well, okay, does it change and by how much? That's the real question. Now, unlike right ascension, if we examine this expression for change in argument of periaps, we see a couple things. We first of all see R and T show up here significantly. R and T show up. In fact, they're the primary drivers. Right? N shows up, but only indirectly. Because remember, omega dot is defined by n. Remember, RT and n are the three components of that force, right? If you remember from the previous slide, right? R, T, and n, right? So this is what we were using before, and now we need the expressions for R and T. Right, and I conveniently wrote them here. And I will also very conveniently not go through the orbit averaging integral, right? Because it's a little bit even more complicated. So just to remember, we have now the expression for omega dot, right? Is a function of theta, right? So if we average this as a function of theta, so we want to express it as a function of theta. Well, we can we move this from omega dot to theta d omega, and remember we had that expression from previous slide. So now what's new? All right. Well, first of all, we multiply by cosine I, and then of course we add these two terms into it. And through some miracle of arithmetic and algebra, it actually simplifies out to something not terrible, right? So these coefficients, right? Here we've replaced p with or r with the r with the polar equation. Right? And we do some complex calculations, which I won't go through, and we get something relatively simple. It has two major terms. One doesn't depend on inclination, and one does. Right. Okay, so where are these coming from? Okay, so let me erase here. So notice that we have three terms. Right. So let's go through them. So radius. Remember, here's your spacecraft, right? And it's got its forces exerting, right? It's got R. Well, actually, in the opposite direction. Right? R. It's got T in sort of the direction of travel, and it's got N, which is pulling it down that way. Right. So we're not going to, N doesn't factor in here, N enters through omega dot, and we'll talk about omega dot separately. So periaps. So periaps, remember, is the point of closest approach. Actually, it looks like it's going here. Periaps. And so how do these forces affect it? Well, let's think about it. R. So if your R is positive, R is pulling you a little bit down, right? Pulling you towards the orbit, right? Towards the center. Well, R is actually right in that direction, so it's pushing you out. The positive R is pushing you out, right? And so if it's pushing you out, if this is your periaps, right? And it's pushing you out, right? Then you're getting a little push that way. And so when you're pushing out, and then when you come back, the next time your periapse is going to be, well, it's going to be a little bit earlier, right? And so if we look at positive r, positive push in the opposite direction, we see that the effect on omega dot is negative, right? So that so positive r implies omega dot less than 0. Right? So in our case, right, we got this equatorial bulge actually pointing in the negative direction. So we're gonna that's gonna end up being so where's that r here? R ends up here, right? That secular term here, negative secular term there is going to end up here, right? So that the sorry, not there, ends up right here. Right? So that that radial component pulls the perigee forward in the orbit, right? Forward in the orbit. Radial component. Likewise, the tangential, right? So the tangential is sort of like radial's pulling it that way. Tangential force is giving essentially the orbit more energy, right? It's sort of like if you're rotating in your orbit, it seems to like give it a little bit more energy there, for example. Of course, that'll be canceled at the other side, but it gives it sort of, if you're giving a little bit of extra push, well, this is no longer, here's our original orbit, right? Giving a little bit of extra push, that's, remember that what that does is that that's an apogee raising maneuver, and so we would expect to see something like that we get to apogee sooner, right? So if we mapped another orbit slightly tangential to that one, right, it would look, yeah, looks awful. That's what it looks like. So here's our orbit. Instead of now getting a little tangential component there, and so, oops, mapping it back that way. And so we have a progression of apsides of nodes in the positive direction for this component. Meanwhile, so that's what we have a note on, tangential advances perigee. And meanwhile, we have the effect of right ascension, right? Changes in right ascension. Now, how it changes in right ascension affect the periapse? Well, let's consider the extreme case, right? So your periapse is fixed in space. So the orbit itself, let's assume the orbit itself doesn't change. The periapse is fixed. But the right ascension is changed from here to here. Now, so what is the argument of periapse? Well, it's, remember, this angle, right, from here to here. Right? And if your right ascension has changed, right, that angle has changed, right, from this length to this length, right? Positive plus delta omega. That's a positive change in delta omega. And the effect on the measurement to this point of periapse has this angle is decreased. Negative delta omega. And that's what's causing this. Right? Of course, in a polar orbit, when I is 90 degrees, you don't have to worry about this. Nothing changes. But just geometrically, a positive change in right ascension causes a negative change in argument of periapse. So that's sort of what all these forces are doing. So finally, we take that expression here, right? Plug in for this term here, and we integrate it over an orbit, right? To find the average rate averaged rate of change of periapse. Okay. So the expression then we get, and I won't go through the derivation, is not much worse than what we had before. There's the terms that come directly from the omega dot times cosine I, and those factor in here. And then there's some other terms which also appear, which are new. But the net over all those three forces are pushing it or T pushing the orbit forward, R pulling it back, so to speak, and then just the geometric change in delta omega. All of those combine until you got a positive effect and a negative effect, where the positive effect doesn't change with inclination. So there's a sort of a scalar effect, and then there's one that does vary with inclination. So to summarize, all orbits have perturbations to the argument of periapse. A part which can't be changed, which is secular, and a part which can be changed, which depends on I. On inclination. Okay. And again, right, here we've got these changes in argument of periapse. Pushing your orbit forward causes the periapse to move forward, and radial terms which cause the argument of periapse to move backwards. I believe that's what it is. Right, so how big are these things? Well, it turns out they could be even bigger than right ascension changes. They can be very large indeed. So up to, again, 20 degrees per day. Our change in argument of periapse, which is huge, right? Huge change in argument of periapse. In let's say 6 days, your orbit could go from the northern periapse over the southern hemisphere, for example, to argument of periapse over the northern hemisphere. 6 days. Of course, that's for height of 0, but it says extreme case. And it decreases as inclination decreases until you get to actually a point where it switches from positive to negative, right? So negative. Positive. And that transition point is called the critical inclination. And it's the point where, of course, this term, 2 minus 5 halves sine squared I equals 0. So if you just solve that for I, there are two solutions, both 63 degrees and 116 degrees. One of which is posigrade orbit, and one which is retrograde. If we look at the effect of J2, so we talked about J2 on, so the big effects are on omega dot and low omega dot. So argument of periapse and right ascension. If we look at the effect on the other orbital elements, the effect is usually minor, especially semi-major axis, because these are sort of energy preserving properties, tends to be 0. Remember, energy is directly reflected in semi-major axis. Okay. So again, we see some variation here, but relatively some secular perturbation in A, but relatively minor. And this may just be due to integration. This is actually this is eccentricity. Sorry. So this is eccentricity. Eccentricity does change slightly, but again, it's a relatively minor change. This is relatively high orbit. If you really want E dot to be 0, then you can use the J3 perturbation. There's a way to create frozen orbits from the J3 perturbation. But we're not covering it. J3 frozen orbit. Look it up. Here's some other, another orbit, high orbit, different orbital parameters. More or less frozen in this case. Right. The secular change, approximately 0, J3 frozen orbit. So typically, if we're freezing the orbit with respect to eccentricity, we look at that J3 coefficient. Again, not going to fuss with it. Here's another orbit with some secular perturbations. Yeah, again, if you want a frozen orbit in eccentricity, you can use the J3 perturbation, but we're not covering it. In that case, you would there are certain values of argument of periaps and eccentricity which lead to a frozen orbit. But again, not covered here. Inclination changes over time. Again, relatively minor. You can see it's occurring here in the second decimal place. We're gonna we generally, and this is for a low orbit, so this is actually relatively large. So we're again not gonna focus on it too much. Not at all, actually. The one effect, of course, that we focus on more than any, perhaps, is this change in the argument of periaps. And because this has significant implications for communication satellites, spy satellites, that type of things. And it's a solvable problem. Right, that's another thing. Specifically, it's a if you don't want your argument of periaps to change, right? Then that's you can use what we call a critically inclined orbit. Right? It's a critically inclined orbit because we're solving this equation equal to 0. Right? And of course, really, all these terms, right? We can't make them 0, so in the end, we have to make this equal to 0. Right? And so, right, we just multiply by 2, and we get this equation here. And there's in fact only 2 solutions to this equation, specifically 63 degrees and 116 degrees. So the only solutions independent of P, independent of A, E, all of these other orbital elements. The only orbital element you can create a critically inclined orbit with is inclination, and there's only 2 critical inclinations which cause a critically inclined orbit. The 2 most famous, well, actually, I guess the 2 most famous critically inclined orbits are, of course, the Molniya orbit and the Tundra orbit. Right. So let's see. Yeah. So what are these orbits? So these, well, I have an example of them in a bit, and I'll talk about them a little bit more at that point. But what are they? Well, if you look at here, this is an illustration of a Molniya orbit, right? So high apogee, low perigee, right? So what are these things? So these are a class of orbits which were designed primarily by the Soviet Union during the Cold War days for several purposes, right? So basically, if you're in the Soviet Union, right? Let's say, where's our Soviet Union here? Say we're launching from Kapustin Yar over here. The problem is that the Soviet Union, right, most of their launch sites, and unless you want to like invade a country and take over their equatorial country and take over their launch sites, most of the launch sites are in high latitudes, right? Right, northern hemisphere, right? Now, this poses several problems. So obviously, the de facto, right? The gold standard of communication or satellite orbits is GEO. Right. So if you want your communication satellite, you would like a geosynchronous orbit because you design that communication satellite to service a particular area of the Earth, and you don't want it wandering over various parts of the Earth, right? So actually, the geosynchronous orbit, the ground track, right, looks like that. Well, that's actually a bad example because who wants to communicate with some island in the Pacific? We'll put a geosynchronous orbit right above, say, the United States, or right above, well, except it wouldn't be there. It would be at 0, right? So that's GEO right there. So that would be the ideal, but it has problems for high latitude countries for two main reasons. First of which is, of course, that if you remember our lecture on launch, right, launch capabilities, right, the GEO has I equals 0 degrees. And if your launch site, right, has, say, phi equals to 40 degrees, the minimum inclination you can launch directly into is 40 degrees, right? So say if you launched from this point right here, right, then the inclination of the orbit is limited to inclinations of 40 degrees or greater, right? So the only way to change that is to have an expensive plane change maneuver. And as we remember, a plane change maneuver of 40 degrees is very expensive, right? Remember, delta V equals 2V sine theta. Theta over 2, I believe it was. Something like that. So sine of 20 degrees is relatively large, so this is actually a very expensive plane change maneuver. And so for the Soviet Union, if you're launching it, you have to do a plane change of 40 degrees. That's a lot of delta V budget. Right. So it's very expensive to do. So actually, GEOs, very high delta V budget. The other thing, of course, is that you're designing a satellite to communicate with someplace in the northern hemisphere, right? Remember our topology, right? This is your local horizon, right? Here, here's your, maybe your satellite tower, right? You get pretty crummy coverage, right? Even if we let's put our GEO way out here, right? So that the maximum declination in the sky that you're going to see that GEO orbit is going to be limited by your latitude, right? So it'll be in like 90 minus latitude, right? So let's see, at latitude of 90 degrees, it would be 0, right? Yeah, so that would be the maximum declination. So if you're a high degree latitude, you're not going to see this communication satellite very much, and it's going to have poor line of sight. You have to go through trees and buildings and all that. Right. So there's two problems, like poor line of sight and high delta V budget, meant that geo orbits for the Soviet Union were not really an ideal choice, right? And so what did they do? Well, what they did was design another orbit called the Molniya orbit, which had some of the advantages of the geo, but performed better at high latitude. So if we go back to the previous slide, specifically, they designed an orbit which spent most of its time. So if you remember, like this delta theta, right, this part of the orbit, it's going to spend, it's moving very slow at this near apogee, and so it spends most of its time in high orbit. It spends most of its time in orbit, spends a little bit of time in low orbit, so it's pretty useless down there. But it doesn't spend long there. So it spends most of its time in valuable territory where the line of sight with northern hemisphere is very good. Right? So 63-degree orbit. 63-degree orbit. So at its apogee, it's above the 63 latitude line, and so good line of sight. Perfect line of sight at 63 degrees latitude. Sorry, that's longitude. So it spends most of its time there and spends very little time out. Conversely, the other application of this orbit was for spy satellites, and so actually in that case you would spend most of your time over the over the United States, I guess, in that case. And there certainly were such satellites, because it's easier to observe Washington, because that's at like 35 degrees latitude. However, right, again, the downside of this orbit is that it needs to have a repeating ground track, because you don't want drift. You don't want to, so basically the Molniya orbits, right, it's very convenient because, right, you're a spy, you can spy on the United States, and then where is exactly 180 degrees longitude away from that, right, well, it's the Soviet Union, and so you can spy over there and report over here. So very convenient repeating ground track for the Molniya orbits. And obviously the period here, right, the period here is not geosynchronous, right, because it's moving over time. So the period here is 1/2 day. Right? It's not a period of 1 day. So it moves a little bit faster. You see it moving with respect to the Earth. And of course, it moves less, right, at apogee. So it hovers above its target location for long periods of time, near almost matching the rotation of the Earth, right? In fact, actually moving a little bit faster than it at some point. And then it comes down here at perigee, where it's not being useful anyway, and it zips through that very fast. And then it comes back here to apogee. Right? It's a repeating ground track. So it needs a repeating ground track, needs to be critically inclined, and needs a period of 1/2 day. There is a version of this for geosynchronous, right, which is the tundra orbit. Again, avoids plane change. So t equals t Earth, right? So the period is equal to the period of the Earth, right? But it's also designed so that it spends most of its time in the northern hemisphere. So it's not circular. It could be circular, and it could have that t equals te, but then it would waste all this time down here in the southern hemisphere when not being useful. Right. So for the tundra orbit, right, the period is the period of the Earth, but you have apogee over the northern hemisphere, where it's being useful. Alternatively, of course, if you're Australia, maybe you want to design your apogee over the southern hemisphere, but that's not the issue here. And you need a repeating ground track, right? So you do have to account for those like omega dots for these orbits. Not a great deal because they tend to be high altitude and not as great an effect. So you get these teardrop shapes. This is periaps. This is apoaps. The tundra orbit versus the Molniya orbit. Two cases of where you want critically inclined orbits. Okay. Critically inclined. Oops. I shouldn't. Critically inclined geosync, sort of, and repeating ground track. Repeating ground track, critically inclined, half period day. So sort of the same thing, it's just the period is half day versus a whole day. Okay. The next special case, which we consider is the case of the sun-synchronous orbits. Right? So the problem, so you design, this is a case where you've designed your orbit to it's sort of like a repeating ground track, but you want it that not only the ground track to repeat, but you want it to be over the same point on the ground at the same time of day, right? So there's various reasons you may want that. Mapping, right? So here's your, let's see. I'm really bad at drawing continents. Here's Africa. Here's North America. There's South America. Right there is Asia. Right. So you want your ground track to repeat. Let's say like that. But you also want it to be, say, over, I don't know, Brazil during the day and over, say, China at night. Or Africa at night. Right. So how do you do that, right? So obviously you got to get the same time of day. So let's see. So obviously in fixed space, right? Here's the sun, right? You design your orbit. Let's say we want to design an orbit so that we're never in the shadow of the Earth. Why wouldn't you want to be in the shadow of the Earth? Well, of course, if you're in the shadow of the Earth, right, no solar power. There's shadow evading. There's other reasons not to be in the shadow of the Earth. The primary one is temperature, right? There's no better way to break a satellite than massive changes in temperature. Temperature changes cause expansion and contraction of physical components. These expansion and contractions can cause fatigue, They can cause something to shatter. They can cause something to freeze your propellant. There's lots of nasty things that can happen if you go into the shadow of the Earth, because the temperature changes are really quite dramatic. That's why all these satellites are always covered with this foil to this thermal insulation. Anyway, so so the problem is, of course, right? You design your orbit here. It's in the sun all the time. The problem is, of course, that the sun moves. Well, of course, the sun doesn't really move, but the sun moves with respect to the position of the Earth. So, for example, here, for example, you design an orbit here, right? And let's suppose it doesn't change with time. That orbit, the right ascension doesn't change. You get this the same orbit over here. Here's Earth. Your orbit, right? Angular momentum vector, fixed in inertial space, right? But the sort of position of the orbit with relative position to the sun, right, has changed, right? So let's say, actually, I don't think any of these cases are shadows. Make another one. See if that gives us a shadow. Okay, there we go. So you move from here, where you're never even close to in shadow. You're always sort of perpendicular to the Earth-Sun vector. Whereas here, you're in inertial space. Your orbit hasn't changed. But with respect to the sun, right, now your orbit's sort of lined up with that Earth-Sun vector, right? If omega dot equals 0. Right. So if that omega dot, eventually you'll move into a different, so this is the sunny side, right? This is the sunny side. This is the dark side, right? You see your orbit in this case is always above the Earth at dusk. And here the satellite is above the Earth at noon, midnight. Here it's noon, here it's midnight. So this is a 6 p.m. orbit, 6 p.m. to 6 a.m. Here it's a 12 o'clock p.m. orbit. Okay. And so a sun-synchronous orbit allows you to design an orbit where omega dot drifts slowly and at the same rate at which the apparent position of the sun is changing. So that now here, if we look at the actual pictures here, that this is like a 3 p.m. orbit, 3 p.m., 3 p.m., 3 p.m., 3 p.m. 3 p.m., 3 p.m., 3 p.m., 3 p.m. orbit. So that this, but this requires, of course, that the orbit change, right? It's right ascension over time, right? Okay, so that's several reasons. Again, mapping, right? Mapping is an important application. If you always want that, the shadow of the office building to always look the same, if you're comparing things, it's intelligent satellite, comparing changes in buildings and so forth, changes in vehicles, something like that. Typically you like a little bit of shadow so you can gauge height. Lots of reasons to have sun-synchronous orbits. So how do we create sun-synchronous orbits? Well, they have to match the parent position of the sun over a day. over a year. So how quickly is the sun changing its right ascension? So that's really the critical question. So here's your planet, here's your orbit, right? And here's your right ascension, right? So you want to, so here's the right ascension of the sun, right? So the sun has its own right ascension. Here's the sun, right? Here is the satellite, right? And here's the first point of Aries. So you want this vector to be constant. So how fast is the sun moving with respect to the first point of Aries? That's the real question. Well, of course, the sun is actually not moving, right? But its apparent position in the sun in the Earth with respect to the Earth is moving. So here, if we look at this this angle here, here's there we go. That angle. It's not changed, right? That's inertial. It's moved from there to there to there. Right. And of course, as you move around, right, it'll go all the way around. That angle will go all the way around. Right. And after a period of 1 year, it'll end up back where it started. And that angle, after a period of years, 1 year, where you end up back where you started, will have moved by an amount of delta omega, equals 360 degrees. Right. So what we get then is that we want our right ascension to equal 360 degrees. Every year. Now, what is a year? Right? How long does it? What do we mean by a year? Well, of course, we mean 365.25 days, but that's not quite what we mean. We get 1 day for free, and so we have to count that as well. It's not actually 360.5.25 days because, of course, the motion of the sun around the Earth gives us 1 day for free. That's the difference between a sidereal day and a regular day. In any case, what we get is that we want, if we divide 360 degrees by 365.25 days, we get that the desired rate of rotation of the right ascension is about 1 degree per day. Or if we put that in radians per second, 1.992 times 10 to the negative 7th radians per second. Yep. So if we now then put that into our formula for omega dot, which we had, let's see, I think I got that somewhere here. Yeah, here we go. If we put that into our formula for omega dot, and then solve for I, right? Then we can, let's see if I can, I probably cannot remember that, but 3/2 NJ2 REOP plus 9. Probably should have put that on the slide. Was it cosine I? Unfortunately, I don't have students here, so I can't remember. Okay, you just cosine I. Actually, I could have just like inverted this formula. There's a 3/2. Oh, and this is P, right? Comes from that. So I invert this. I solve for I, and and we get that and this is of course. Divide desired, and this is n mu over a cubed. Okay, so yeah, so we solve for I, and we can get the inclination for a given A. And of course, given E, we can solve for the desired inclination. So a sun-synchronous orbit depends, of course, on choosing a specific inclination, but that's not necessary. You could also choose, for a given inclination, you could choose a critical E as well, or a critical A. So here we get the sun-synchronous inclinations as a function of altitude. So unlike critically inclined orbits, the sun-synchronous inclination does depend on altitude. Right? So you can actually line these things up. You can choose an altitude where you can get a sun-synchronous critical inclined orbit. And we see that value as the A is increasing here. And you can see also they're relatively high right here. This is greater than 90 degrees. So near polar orbit. So this critically inclined, these sun-synchronous are typically in near polar orbits. And that's so that delta omega is small. If you remember, if I is small, remember that delta, or that omega dot, remember, was about 5 degrees per day or something, 5 to 10 degrees per day. So obviously we want it to be 0.02. We want it to be 1 degree per day. So we have to have in higher inclination orbits. So here's just an example Landsat. This is a mapping satellite designed relatively low Earth orbit, right, about 700 kilometer altitude. And because it's mapping, you want to maintain that sun-synchronous nature. Same time of day wherever you're flying over. So in this case, we get A. Right, we have A. We can figure that out from the perigee and apogee altitudes. Right. We can likewise figure out eccentricity from periaps and apoaps. Right. So we got those two are fixed, known. And so that gives us immediately the parameter of the orbit, gives us the mean motion, n, and of course J2 is known. And so if we plug this into the formula, this is known, this is known, this is known, this is obviously known, and so we can just find the inclination of this orbit, 93 degrees, so near polar. And that's just to bring this change in right ascension down. The next example that we give here is the Molniya orbits, one that we talked about a great deal. I think I have some background here. Geosynchronous doesn't work well for high latitude. Typically used for sensing and communication satellites, where you want to live most of the time over your coverage area. You want your periaps to stay over your apoaps to stay over your coverage area. So you want omega dot equals 0. Right. No big delta V. Reduce your delta V budget. Obviously, it's not going to spend all your time over your coverage area, so you've got to have a constellation. We haven't talked about constellations very much. They're groups of satellites in similar orbits that work together. They can communicate with each other occasionally. All right. So if you have 3 of these satellites, one is going to be have a good line of sight at all times. Also used by the Soviet Union for U.S. observing satellites and presumably vice versa. Actually, I think, if I remember, Trumpet is in a Molniya orbit. That's a U.S. spy satellite. Let's see. And then we could also get tundra orbits as well as Molniya orbits if we want geo. And they have to have a repeating ground track, but we're not going to talk about that. Right. Technically, a Molniya is a tundra orbit with semi-synchronous, but okay. Anyway, so we want sun-synchronous. No, wait, we don't want sun-synchronous. We want the right ascension for the purpose of having a repeating ground track to process at a certain rate. I just made up this number. For having a repeating ground track. Again, made up. I don't know that that's actually a satellite. Let's see, what do we got? Yes. So, we've got the period, right? Period of the orbit, which is 12 hours. Obviously, we can use that to solve for mean motion, mu over a cubed. And from that, we can combine these two to get the semi-major axis. Right? So period leads to semi-major axis. Next, critically inclined. Right, mega dot. So we get to choose now 63 or 116 degrees. Notice from our formula for omega dot, where's our formula for omega dot? Yeah. I think there's a negative sign in front of that. So from our formula for omega dot, we want, if we want this to be greater than 0, we want cosine I to be less than 0, right? And so we want, if we want cosine I to be less than 0, we want I greater than 90 degrees. Right? This is for the other slide, of course. Oops. And so if I go back to that slide here, hopefully, that will line up with what I said here. So we want omega dot to be less than 0. So we want cosine I to be greater than 0. So we want I to be less than 90 degrees. Again, I probably should have put the formula. Oh, I did put the formula here. There it is. Yeah. So we want cosine I to be greater than 0. So we want I to be less than 90 degrees. Okay. And so we now have, right? This is fixed. This is fixed, obviously. Fixed. The only thing we have that's not fixed is eccentricity. And so we're going to use that to determine this. Right. So basically what we've got to do is invert this equation and solve for E. And that's this formula here, right? It's ugly, but what you're going to do. We have all this this information. We've got A, we've got N, we've got I, we've got omega dot, and so we just plug in all those numbers. Don't forget to make this, remember this is negative 0.2. Or negative, I guess, what was it? It's actually, yeah, negative, no, sorry, not that. We got to convert this to radians. Okay, don't forget to convert to radians, because obviously I didn't write it down. To convert to radians per second, right? And if we do all that, we get that the required inclination is 0.7459, which is actually like an extreme case of a Molniya orbit, but what you're going to do. Yes, so yeah, make sure that the units match those of omega dot. Yeah, radians per second. Okay, so I think that's the last slide. Yes, in this lecture we've covered the J2 perturbation. Well, we've covered the Earth oblateness, right? The effect on mu, the change in mu, the disturbing forces, the effect of that on omega dot and little omega dot, and finally brought that back to the applications, specifically design of critically inclined and sun-synchronous orbits. Right? So this concludes our section on orbital perturbations. Our next lecture will be on the very juicy topic of interplanetary mission planning. So if you enjoyed this lecture, you'll love that. If you didn't, and I know there is a subset of people who would think this is very boring and mathematical, stay tuned for our section on interplanetary mission planning, which will have lots of fun things like gravitational assists and mission to Mars and stuff like that. Okay, so at that point, I'm going to conclude the lecture and sign off.